Welcome back, friends. We'll talk today about heat engines and the other law of thermodynamics, which is related to heat engines. Okay. Heat engine is, in heat engines we have a conversion of heat to work. When a system undergoes cyclic process. What is the system in this case? System is the working substance. For example, in the automobiles, fuel, vapor and air, and for example, steam in the steam engines. Okay. And maybe other things. The system, in the process of the work being done, undergoes several processes. It absorbs heat Q1 at high temperature T1 from an external reservoir. This is the hot reservoir from which the heat is extracted, and then the system releases heat Q2, okay, to an external reservoir at a lower temperature T2. Sorry, it's got to be T2. Okay. So then the difference of these two results by the law of conservation of energy into what is called a work done. Okay. Work done W by the system is transferred to environment via some arrangement. For example, that arrangement could be a working substance, maybe in a cylinder with a moving piston that transfers mechanical energy to the wheels of a vehicle via a shaft. This is how it happens. So, the schematic diagram is simple to understand, that a hot reservoir and a cold reservoir. Okay. Heat is taken from the hot reservoir and given to the cold reservoir. And the difference is W, which is the work done, which is equal to Q1 minus Q2. And then we repeat this cycle. The cycle is repeated over and over and again so that a certain work is accomplished. Okay. The efficiency of this engine is eta equal to the work done divided by the total heat which has been extracted from the first reservoir. And since W is equal to Q1 minus Q2, if I divide this Q1 minus Q2 by Q1, I'll get it 1 minus Q2 upon Q1. The value of eta, you can see, can be equal to 1 maximum if Q2 upon Q1 is equal to 0. Okay? Q2 upon Q1 is equal to 0, and since Q1 is not equal to 0, therefore Q2 has to be equal to 0, which is a remote possibility. And that is why there is some cycles and some discussions that are going to follow in the heat engines. Okay. So the efficiency of the heat engine, eta is equal to 1 minus Q2 upon Q1. Now eta will be 1, that is 100%, if Q2 is equal to 0, which is not ever possible. Not possible even if we eliminate losses associated with the heat engines. Okay. However, eta is equal to 1 is not denied by the first law, which is basically the law of conservation of energy. Now let us take up the reverse of the heat engine. That's called refrigerators or heat pumps. Okay. The working substance is usually a gas. And as I've shown over here, the system, here we are taking Q2 from the cold reservoir and giving Q1 to the hot reservoir. Reverse of what happened in case of heat engines. And of course now work has to be done by the environment so that there is a transfer, etc. There are 4 simple steps. Step number 1 is sudden expansion of gas from high to low pressure, which cools it and converts it to a liquid vapor mixture. What happens? The second step is absorption of the cold fluid of heat. That is, the cold fluid absorbs heat from the from the region to be cooled, converting it into vapor. So this is the second step. The third step is heating up of vapor due to external work done on the system. And the last step is release of heat by the vapor. This is the work which is being done. Release of the heat by the vapor to the surroundings. Okay. So what happens? The cycle completes. And then we repeat it, and we'll talk about the coefficient of performance of now. The refrigerators are small chambers from where you take out the heat. And if we deal in rooms or set of rooms or buildings, etc., in the process of what we call conditioning the air with a fixed temperature that we deal in, then those things are known as heat pumps. It's just a matter of vocabulary, and we deal in this further. So for the refrigerators and the AC performance, the coefficient of performance is defined as Q2 divided by W. Okay? And the conservation of energy says that Q1 must be equal to W plus Q2. So if I substitute that, then the coefficient of the performance of the fridge is Q2 divided by Q1 minus Q2. And we see that the alpha could be greater than 1 or more than 100%. The coefficient of performance of a fridge or a heat removing body. Okay, so this is the, whereas eta can never be more than, even can never be equal to 1. Okay, now we pass on to the second law of thermodynamics, which gives us a fundamental limitation to eta and alpha. Okay, here we have two statements, one by Lord Kelvin and Planck, and alternately by Clausius. They were great performers in science. They were great scientists, of course. Clausius studied the heat engines, etc., much before many things came, and many other things were explained for thermodynamics. So Kelvin Planck said that no process is possible whose sole result is the absorption of heat from a reservoir and complete conversion of the heat into work. So complete conversion of heat into work is ruled out by Kelvin-Planck statement of second law of thermodynamics. Clausius, on the other hand, is giving a similar statement that no process is possible whose sole result is the transfer of heat from a colder object with a lower temperature to a hotter object with a higher temperature. In fact, both these statements are one and the same thing, and they supply to what's known as the second law of thermodynamics. So now we have three laws of thermodynamics we learned. Zeroth law of thermodynamics, first law of thermodynamics, which is nothing but the law of conservation of energy, and the second law that heat cannot convert completely into work. So there is some kind of chungi which is taken in the process. Okay, so it is taxed by the system, and similarly it's not possible to transfer heat from a colder object into to a hotter object. It's Clausius. Now we wish to elaborate on that and would like to learn about the processes which are called reversible and irreversible. The reversible and irreversible processes. So suppose there are two states. One I describe as the initial state and another I describe as the final state with the thermodynamic variables defined. So if I want to go from the initial state into the final state, the system absorbs some heat Q from the surroundings and performs work on it. Now the question is, which we are going to address further: can we reverse this, and can we obtain the from final to initial without some other thing happening in between? So to study the reversible and irreversible processes, okay, we saw that a system goes from I to F, initial to a final system, and absorbs heat from the surrounding and performs a work W on it. Now the question was, can we reverse this F to I? So in most processes in nature, this kind of a cycle is not possible. Spontaneous processes in nature do not subscribe to it. Okay, whatever processes are there in nature. Now some of the examples are, for example, the base of a vessel on an oven is hotter than the other parts, and if the vessel is removed from the oven, then heat is transferred from the base to the other parts, bringing it to a uniform temperature. Ultimately there is a uniform temperature, and eventually it cools to a temperature of the surroundings. Antata, eventually antata, in the end. Okay, now this is not reversible. For example, also not reversible is the free expansion of a gas. If the gas, like we did, has a vacuum associated with it and there is free expansion of gas, it's not possible that the vacuum is created and the gas goes back to its original condition. Diffusion of a gas leak. For example, if the gas in your kitchen, it leaks, diffuses, and then you cannot bring all those molecules back to obtain the gas that was. Similarly, in the combustion of mixtures, For example, the gasoline plus air, etc., and the combustion is there, then you cannot bring back this reaction. Okay. So, let us see as to what are the causes of irreversibility. Why things are irreversible? They are not reversible. One of the things is that the systems, they go to non-equilibrium states, and therefore there are losses, have to be lost. Number two, friction or viscosity in the case of fluids and other dissipative effects, they also don't allow reversibility. Okay. So reversible process is an idealized notion only, because there has to be a quasi-static, as if it were static, and this has to take place very, very, very slowly. Okay. It is a basic concept of thermodynamics. So reversible and irreversible are two concepts of thermodynamics. Like we have the processes in chemistry, there are reactions which are reversible and irreversible. So we have discussed this in the perspective of thermodynamics. The ultimate lecture, the next one, that is going to be about Carnot engine and the Carnot cycle and the efficiency, etc. We'll see that in the Carnot engine, the eta cannot be equal to 1. It has to be less than 1, and there is a calculation of the efficiency, etc. And the best engine is, the most theoretical best engine possible is Carnot engine, and no other engine can have the efficiency equal or more than that of the Carnot engine. This is what we are going to talk about in the next outing. Okay.